Thank you so much. Thanks for very kind introduction and thanks for having me here. If possible, can we also dim this light? You would appreciate results more. Okay, perfect. Thank you. Thank you so much. All right. Okay. All right. Very excited to be here. This is my first time visiting Philly, and it's a very beautiful place. So I've been here only since last night, but love the vibe overall. So today I'm going to talk about generative image models. And the question that I'm interested in asking is, uh, are they like illusion or are they actually doing something grounded in reality? Okay. All right. So first, big point, computer vision is flourishing. We all know that. We know the tremendous progress that we have seen. So if we look back, from 1960 to 2000, we had like simple edge detectors and we had early breakthroughs in the face detection with Viola Jones and eigenfaces. Moving forward, and from 2000, there's a typo, okay, from 2000 to 2010, the era was mostly about handcrafted features where we had SIF and we had this, we had Hawk features and so on, which we use for several downstream computer vision tasks like detecting objects where they are segmenting them. Then in 2012, we had this big deep learning revolution with AlexNet, and we also had this nice, amazing data set from Stanford, ImageNet, where we showed early promising results on doing high-level semantic reasoning tasks like detecting 1,000-way classification, and this was one of the big breakthroughs. From 2015 to 2020, we saw tremendous progress in object detection and segmentation. Like many people believe that it's almost saturated, that we have now SAM, we have now Theta, we have so many different things where different models like RCNN, fast RCNN, mask RCNN, so many different things came out, which showed that we can get really good segmentation and detection. Fast forward to today, what I call this is a generative era or the generation era. We now have models that can generate hyper-realistic videos. And the questions in computer vision has also changed. Traditionally, what we were interested in asking is, what objects are in this image? So we had the segmentation models where we call object detection models where we detected which objects are there in the scene. So there are 3 shapes, 1 dog, and we can nicely detect them. And then we also can segment them appropriately at instance level. Now, the question that most of us are interested in is, can we understand and manipulate the world? So here is one of the very first attempt towards this goal. So this is a recent work from collaboration with University of Washington, which was published at ECCV, where we show that we can convert this nice static table in the scene to a dynamic bonfire without any training, everything just using existing pre-trained model, understanding what is happening inside the model and just making few changes to make it work. So coming back, what has changed? We now have very powerful image generative model. If I tell you like 4 years or 5 years back, or even someone tells me that this image is a generator, it's very hard for someone to believe. Like you can look at the water droplets on the person, you can look at the hair strands on eyes and everything, all looks hyper realistic. It's very hard to believe that it's something very generated if someone had told me back in 2022. Now we have models, it's just like tap of water where you turn on the tap and you get water. Same like you just give a text prompt and output you get is like an image. And all these images look very realistic. So on the left, you see like nice indoor room with light coming, natural light coming from the window. On the extreme right, you see like a landscape, a photograph of a landscape taken by someone like a professional photographer. In the middle, it's a futuristic city with neon lighting, which is something imaginative. We all get this result just by a simple text prompt. And we have this new models. This is OpenAI Sora model where you give like a dense caption where you say that there is a stylish woman walking on the Tokyo street and so on, and you get like a nice, beautiful city of Tokyo in the backdrop, and you see this woman walking with all the details. So look at the reflections onto the road and so on. They all look hyper realistic. So the question is, do this model understand our world, or they are doing something which is unimaginative, and something which is very abstract, which is very difficult to comprehend. So my research is about using these generative models to prove physical understanding. I was having earlier discussion with Antonio today. Here, the physics understanding may mean different to different people. At least in my research context, physical task that I'm interested in is lighting, as Ustaz pointed out, lighting reasoning and scene geometry reasoning. These are physical phenomena because the light interacts with the surface, and that's what we perceive, and that's what the camera perceives, and that's what makes an image. So my research explores primarily these two tasks, like how good these models are at lighting reasoning as well as geometry reasoning. And second, mostly I focus on two-part investigation, what they know and what they don't. What they know will tell us to figure out how we can use this knowledge to improve our downstream task. What they don't know will help us figure out how we can improve these models further. Now, let me take a step back further, and first let's try to understand how our images
We're
form.
not exactly cavemen anymore.
So if you look at it, images are like 2D projections of the 3D world. Okay, this is oversimplification. Let's also see another toy example. So here is a simple scene that I rendered in Blender where there are 4 objects like cones, cylinders, spheres, and so on. And there is a spotlight that is falling onto the scene. Now, imagine there's a camera here which takes a snapshot and we get this image, right? Now, in computer vision, we have only this 2D pixel grid. And using these pixels, we want to understand what is happening in the scene. We want to understand what objects they are, what are the spatial arrangement they are, where the light might be coming from, what is the geometry of the scene, and so on. And humans can perceive this everything very easily, like all the 3D shape, materials, and their arrangement in space. So how do we teach our computer vision models to do the same thing? So this has been a problem studied from decades since the 1960s, when the computer vision field has evolved. So big breakthrough, in my opinion, came with this concept of intrinsic images from these 2 pioneers, Harry Barrow and Jay Tenenbaum on the right that you see on the screen, where they came up with this concept of intrinsic images. What they said is images can be decomposed into fundamental scene characteristics maps or intrinsic maps, which can be combined to form the final image. So here, the image that you see, so this is 1978. As you imagine, you don't see nice photo hypercolor images. So you see a simple scene where there are certain objects. Now you decompose scenes into 4 different parts. One, which is light independent, what they call reflectance or albedo. We'll get into that in next few slides. And the other is illumination or shading. That is what is dependent on lighting. And the third is orientation, like every pixel surface orientation. Today we call surface normals. And last is the distance, like distance from the camera. So today we call it as depth maps. So coming back to the toy image that I showed you earlier. So if we decompose this scene, you can clearly imagine, you can clearly guess that what the albedo or the light independent components would look like. So there's a red cylinder, there's a yellow sphere, there's a cyan cone, and so on. And you can also anticipate, or you can predict, since you already saw where the light is coming from, you can clearly predict where the shadow or the illumination effects you might see on the scene. And at the bottom, you see the surface orientation and the depth maps. So here, in the depth maps, the darker pixel means it's closer to the camera, and the lighter pixel means that it's farther away from the camera. Now, in graphics, we do this like, the goal is kind of like inverse, where given this intrinsic or inverse graphics maps, we want to reconstruct the image, or render the image, render this image back. So why this is an interesting task? Let's say if I want to relight, what I need to do is, so I had the spotlight at the right. Back then, if I move to the left, I just change the shading map and I get a relit scene. But in practice, this inverse graphics approach really doesn't work. So this is a fantastic thesis from Zhenqin Li from UCSD, where one of early works which shows that how we can use inverse graphics representations for neural rendering. But if you look at these results carefully, there are a lot of rendering artifacts. So here, if you see, there are ghost artifacts highlighted in the red. And if you notice in this purple box, there are missing semantic regions. I'm not sure if it is visible on the screen here. There are like patchy artifacts onto the wall. So there are rendering artifacts which are difficult to control because the errors can come up from different inverse graphics maps, and it is it might lead to rendering artifacts. Okay. So why is relighting hard? So I showed you two simple example. Here is another example where it's a simple indoor layer. Yes.
Your rendering, you mean your computation of the scene and like volumetric rendering or network computes?
Yeah, I didn't get into the details. So in this particular work, they use both. So you have neural networks, which gives you inverse graphics maps. Then you have a rendering engine like Unity or Blender, which you use them to render the images. So here they are rendering sphere balls composite just to see how you can relight and so on. The point I wanted to make is that this neural rendering was very popular back then and changingly made it quite evident that these are something useful representations to have. But unfortunately, we still have these errors which are difficult to control. So why is relighting hard? First, most of the time, what we look at is simple control scene. And in reality, this is also a simple scene that you see. There is no furniture. It's a simple indoor room. But you can see that the light interacts very differently in the simple setup. So what are the assumptions that we make? We make first a Lambertian assumption, meaning light reflects uniformly, which is not true in reality. Why? Because real surfaces may have specular highlights, they may have variable roughness, and the materials might be complex and light interacts differently, so we perceive differently, which makes this problem very hard. Another thing is the complexity of the light source itself. We may have like a point light source, like a sun, far away in the sea, or we may have like an area light source like the chandelier over here. And the color of the light might also change. And the other thing which many people might not pay attention to is there might be intensity fall off, meaning pixels that are closest to the light source are intense, where pixels that are farther away from the light source are less intense. So this intensity, you need to understand all this complex phenomena and then learn to model this, which is kind of hard. And there are other global indirect effects. Like here, if you notice the color of the wall, they are the same color. We know that they are of the same color, but they look different in the images. And you need to disambiguate it and you need to figure out how to do it. And you can also notice there are cast reflections from the chandelier, which you need to figure out. And here in this scene, they might be seen where you may have water droplets or you may have water. There may be some scattering effects, which are again very difficult to model. So then how do we solve this relighting task? So looking back, I showed you some realistic images from generative image models. And these images show plausible lighting. You can see that it understands natural light, the light coming from the windows. It also knows how the scene might look like in the sunset. And it can also kind of predict what the scene might look in the futuristic setup with neon light. So there is a hint of plausible lighting understanding within these models. So the question is, can we tap into this knowledge? So hypothesis, which we are operating on, model learns lighting physics implicitly. Now, can we access this knowledge? Why this is important? If we understand how models represent this light, we can control it, and then maybe we will be able to relight it. Now, taking a step further back, first, let's try to understand what are these generative models. So generative models have been studied from very long time, but I think big breakthrough came in with this generative adversarial network, GAN, from Ian Goodfellow, which deservedly has got the test of time award at this NeurIPS. So how this GAN framework works, you start from a simple noise, you pass through some generator, which makes an image. We call this fake or generated image. Now you have pool of real images. Now there is another network discriminator, which is trying to predict whether the image that you get is generated by a network or it's actually from real world. So it's a two-player game, and it's a min-max operation where the goal of the generator is to fool the discriminator, and the goal of the discriminator is to get to clearly figure out which is real and which is fake. In doing so, the generator is able to learn to generate high-quality images to fool discriminators so that the generated images look real. 5 years down the lane, another big, in my opinion, big breakthrough came in generative model is with the style GAN from Keras et al. From NVIDIA. What they did was they did a simple change to the model. They did a couple of changes, but more simplistically from architectural point of view, one simple change they did is instead of directly sending noise to the generator, you first send them through some mapping network, which is a bunch of multi-layer perceptron, like 8 or 10 layers, which you get some high dimensional code, then you feed it through generator, and then the rest of the process remains the same. So doing so first, we get high quality results. You see the GAN results on the left and style GAN results on the right. As you can clearly see that these are much more high resolution, photorealistic as compared to the left. The other nice thing with the style GAN architecture is that with every year, the results kept on getting better and better on complex scenes like indoor images. And most importantly, the mapping network that I talked about had very nice interpretable latent representations that you can manipulate to get different layouts of the same scene, or you can manipulate images to generate realistic editing of the same scene. So on the left, you see a latent code manipulation, which changes the layout of the bed. In the middle, you see some mid-level blob manipulation, which you can encode in this images. So you get nice, again, layout changes. And then you can also combine with neural radiance field or other 3D aware rendering to get like 3D aware manipulation. So now question again, coming back to lighting, can we relight using the style GAN architecture? So here is our first work, which was published at last year's CVPR. We call it Stylet GAN, where the goal is to use style GAN to relight images. Before we get into detail, I want to first show results and convince you that we can get diverse relighting just by manipulating latent codes within the style GAN. Notice that the major changes that you see in the images are due to lighting. The overall layout of the scene does not change. There may be small local geometry changes. That is kind of a limitation here, but most importantly, what you see is lighting changes. The albedo or the color of the scene does not change, and the geometry layout is preserved. I'll let it play for one more time. So how Stylet GAN works? This is again a schematic, a different schematic of the style GAN that I earlier showed you. In style GAN, you had this nice you had a nice, and then you had a noise. Then you feed it through a mapping network, which gives you some style. They call it style codes, which are disentangled representations. And then you feed this through a synthesis network that makes an image. Now, what we did different in Stylet GAN is that instead of generating just one image, we ask Stylet GAN to generate a bunch of images. And the way we do it is we add what we call lighting directions to the original style code, just like an additive addition. It's like a latent noise that you add to the model, and you synthesize a bunch of images. And we call this relighted images. And the way we ensure these images are relighted is we use an off-the-shelf image decomposition model that decomposes this batch of images into two parts that we earlier talked about: albedo, that is light independent, and shading, that is light dependent. Now, what we want from relighting is the light independent component should not change as lighting changes. So we apply a consistency loss, that is, or invariance loss. All this batch of images should have the same albedo. And then we have a diversity loss, where what we say is that in low dimensional, all this shading that we get from different images should be linearly independent. So you can think of this as a diversity loss. Now we need to take care of one minor thing, is that in neural networks or in deep learning, if there is a chance a model can cheat, it will cheat. So this is like a rule of thumb that we observe in this as well. So in order to make sure we get diverse relighting, what we do is we also train a classifier that takes two images as input, an image and a relit image. And the classifier goal is to predict which lighting direction was applied. So for example, if I apply a red direction and I take the relit image that I get from the red direction, and the classifier has to predict that, okay, the red direction was applied. Right. So simple categorical classification.
So you have a discrete set of lighting directions that you're applying for every image in your data set?
So we have discrete lighting, yes, but they are applicable for all images. So it's a general lighting directions that can be applied to any images.
But within the context of each image, like the examples that you showed involve like lighting one of the table lamps or one of the, bedside table lamps and things like that.
Yeah, we'll get to that. Yes,
Okay.
that's a good question. So here, the one thing to note here is that the GAN model or the image decomposition model are pre-trained and frozen. The only thing that we are learning is this classifier and this light directions. And the model is frozen. And the rest of the thing, and what we find is that if you just do this optimization on thousands of images, we can find nice lighting directions that are able to relate scenes. So here are some qualitative results. Yes.
I was trying to think when you're talking that you want to preserve all the video specific information in the style codes and on the lighting specific information in the lighting feature vectors context that we give. What in this architecture prevents the lighting information from sneaking into the style codes?
Can you repeat what
In this architecture, how do you ensure that the lighting specific information, the lighting direction, doesn't sneak into the style codes?
So we don't have any constraints over it. We just only control we have over is the hyperparameter on how much loss that we want to enforce. So it's empirically we try to adjust how much consistency loss we want to apply and how much diversity loss that we apply. And then we have certain ways of evaluating whether we got good relights or not. And that's it. There is no other constraints that we apply to the model. So there may be a leakage of information, but since we are not updating the model, the only information that we are learning is lighting direction, and the blue code that you see is image specific. So this is what dictates what image is going to be generated.
Like a style code of one dimensional, lighting direction was another dimension. Then the correlations between these two dimensions are precisely the information leakage. So disentanglement between these two kinds of information is very hard to achieve.
That's true, and they have to be related because lighting cannot just appear; it has to be dependent on the scene, and we are exploiting that fact.
So that is the job of the synthesis network, right? To modify the lighting context,
Right,
in a way that is suitable for the style code,
right,
in your image.
right.
So a priori, like if you were to think of style codes and lighting directions as two different latent factors or contexts,
Right.
they got to be disentangled.
Correct.
And I was curious, like whether you've checked whether they are actually disentangled.
Yes, which I'll show in next few slides with the results. So here are qualitative results. First, I'm showing just two relight. They look kind of similar, but there is a subtle difference. Notice that here the bedside lamps are switched on. In both cases, the difference between the two is in the first one, there is an orange tinged light, and the second one, there is a white tinged light. It's not obvious from the second, the top row, but if you look at the bottom row, you would notice it. And in the third, fourth, fifth, in the third lighting direction, there is a strong directional light coming from the window, and you see like a nice glossy patch onto the floor. In this case, the window is not visible, so you see a nice glossy patch onto the wall. In the fourth case, the overall brightness of the room increases because of the light coming from the window, and there might be an invisible light source that is invisible to us. In the last one, the overall lighting of the scene is suppressed, so you see like a not so well lit room as compared to the original scene. Okay, so coming back to the question, so one thing to notice here is that, each direction comes from a individual lighting vectors that I showed you. So what this means is that each direction means independent lighting encoding or representation, some understanding of lighting in some semantically meaningful way, which a GAN model understands, which we do not have control over. This is found a priori. So we just look at the bunch of, in our case, we experimented with 16 directions. We look at what type of relightings we get, and we observe that these are kind of disentangled representations and then we are different. So we do not have any control over whether they are disentangled or not. This is what we find empirically, that these lighting representations are disentangled. Yes.
Lighting direction, because lighting direction implies that you're changing probably the light source position in your scene, is it? Or because, as I understand, you have now these 16 directions that you can do. And
So,
probably they
okay,
latch on
I
to-
see the confusion.
I guess they latch on to different whatever lighting sources that your GAN generates, and then you can control those 16 sources, but.
Yes. So here lighting and direction are independent to each other. They're not related. The direction is direction in latent space that I'm navigating through. And lighting is this. This is like a standard terminology what people use in the literature. We just trying to follow it, but I can see the confusion. So here the direction it has nothing to do with the how light is moving into the scene. So direction is just in what direction in high dimensional space that you are moving.
In a sense, so would you agree with the intuition that let's say your GAN generates a scene with 5 lamps.
Right.
There are 16 directions. These
Uh-huh.
16 directions will probably latch onto the 5 lamps and change different components of the light.
Right. So it's a complex phenomena. You can have there may be a linear relationship between the two different light sources and so on. And this is what we exploit on the video that I showed you earlier was just interpolating between these 5 different directions. So if you linearly simply interpolate between 5, this 5 lighting direction, you get like a nice video. The model is not made to generate video, but this has nice descent angle properties which you can linearly interpolate and you get a video out of it. So here are more results just to show we can switch on bedside lamps. The model needs to understand where the lamps are. We don't provide any semantic information to the model. The model automatically figures out that it needs to switch on the lamp. There needs to be a direction light coming from the window and so on. Make a couple of observations. Okay, StyleGAN can relight scenes, but one limitation is that it only works on generated images. What we want is we want a relighting model that works on real scenes. But the good thing is the generative model knows about bedside lamps and windows, which are like plausible light sources. And it can create direct and indirect illumination effects. If you notice in the video, you can see that there is when the lamps are switched on, it knows that there has to be a local gloss or specular highlight that needs to be added. And it seems to interact reasonably well with the scene layout. So this got us thinking, so, okay, this worked well, but this was mind-boggling for us because relighting is not, as I described earlier, it's not so easy. You need to understand there are so many complex interplay between scene geometry, light sources, and the surface layout. So we asked this question, okay, StyleGAN can relight complex scenes, but how is it doing it? Is it manipulating some abstract representations of our world, like maybe like a Mondrian, Kandinsky, or your favorite painter, or some complex features which we don't really understand? Alternatively, they might just be dealing or manipulating intrinsic images that we talked earlier about. Albedo, shading, surface normals, and depth. If this is the case, then we should be able to recover them. If these models are dealing with intrinsic images under the hood, as we saw in graphics, these are important inverse graphics representation that renders an image. You can think of generative models are a rendering engine, they are generating images. So if they are able to generate images, and if they are able to understand our physical world, then we should be able to recover them. Okay. So this is, yes.
Can I ask why it is a priori a reasonable hypothesis that we should be able to somehow add a vector to these style codes? Like, why should it be added? Was it just kind of a hypothesis that you ran with and it kind of worked out, or is there a reason to expect this a priori?
So we wanted a simplest solution to it, and a lot of work earlier in StyleGAN manipulation. What they do is you manipulate layer 1, layer 2, layer 10, and so on. To me, it's unscalable. Like every year you get a new model, you can't repeat this process. And we wanted something as simple as possible.
Right, but it still relies on the StyleGAN having learned an embedding somehow that does encode it in this convenient way.
That's right. So this is based on observation from other research where people have shown that, okay, this descent angle representation naturally emerges and you can find linear vector embeddings that you can move in and you get some relativity. But it was not clear how to get for relighting. And here it appears, it took 2 years of work to figure out exactly the right, one thing which we didn't get into is what intrinsic image model to use. We just kept it under the rug. Right now, we assume that we are using intrinsic image model. So the choice of intrinsic image matters a lot. We'll get into that if we have time towards the end. And we wanted to find the simplest and most elegant solution possible, because that's the only way you can tell the model has this knowledge. If you fine-tune the network or if you retrain the network, then it is unclear if this knowledge is present already encoded in the model, or is it because of byproduct of your retraining. So this is the only way to find consistent evidence that you're not touching the model, you're just traversing in the latent space, and doing so you're able to find. That's the stronger evidence, in my opinion, to say that the model has understanding of lighting, rather than finding, okay, if I change this layer, you get this output. If I change this layer, you get this output, which may work, but is not scalable.
Yeah, we can talk about it offline, but yeah.
Okay. So then, in a follow-up work, we show that indeed this is the case. StyleGAN knows about normals, depth, albedo, and mode. So first, let me again show you results of recovered intrinsic images from StyleGAN. So here is a normal, depth, albedo, shading, and also we can segment like lamps that are present in the scene. Now, at the bottom, you see state-of-the-art models, supervised models back in time, during that time, where if you notice carefully, the lamp segmentation is much better than the SOTA segmentation, which is trained with label data set. It should, because the model put them there, so it should know that where the lamps are. If it is, the goal is to segment lamps, then it should be able to segment all the lamps. For other intrinsic representations that you see, albedo shading is what we find is that overall it's best as compared to SOTA model. Whereas for normals and depth, it is not as good as SOTA models, but it preserves fine details. Okay. Here is another example, which kind of shows that we can get nice intrinsic images directly from StyleGAN. So how does this intrinsic image recovery works from StyleGAN? Again, we use the same StyleGAN, the same network that we saw earlier. Now, what we want is, we want to find latent directions or latent embedding for each scene property maps or each intrinsic images. So we have this purple for normal, we have this orange for albedo, for depth, and so on. And the way we find this direction is we use off-the-shelf intrinsic image predictor maps. So you use an off-the-shelf model that predicts a depth map. You use an off-the-shelf model to predict a segmentation map. All these are frozen. And what we do is we just simply apply a regression loss and update this scene property direction. That's it. So here off-the-shelf network is a model that is pre-trained by someone else that learns to predict depth maps, surface normal maps, albedo, and shading. This is used to guide because we need to figure out what we are searching for.
The one that predicts albedo off the shelf, what you call off the shelf, is something where somebody provided ground with albedo.
So albedo shading is, I didn't get, it's a model from our previous work. It's an unsupervised model, but normal depth segmentation is a supervised. What we want is we want some signal that we are looking for to guide the latent search process. So either you can use a ground truth if you have, but since we are dealing with generated images where we don't have actual ground truth, we have to rely on some model predictions that will guide us this search. So we use this pre-trained model, a normal, we use only data back in time. For depth, there was this Zoe depth, and for segmentation, the segmentation model that I earlier showed. And we use this pre-trained model, and we need like maybe few hundred pseudo ground truth or pseudo ground truth label to search this. And what we are, notice that what we are optimizing again is only the scene property directions, which in turn optimizes the output that you get, normal, depth, albedo, and shading.
So the synthesis network by default doesn't predict these 5 different channels, right? It just generates the image.
The synthesis network is far from?
It just generates the image, right? It doesn't generate by default.
Yes.
So this is something you're adding in by getting this modified style code, right?
Correct. So we just add a modified style code, and when we feed this red code, instead of getting images, we want corresponding surface normal, depth, albedo, and shading.
So now the question is, why is this why is the direction kind of continuous number instead of like a categorical variable? Because somehow, as I understand it, should be just like, now I want my network to create normals, it should be like, now I give it this index, now I want to give that, now it's this index.
Correct.
Why is it a continuous in these property directions, like what is the continuous boundary?
Why they are independent? Can you repeat that part?
Like why are the same property directions that you're inserting into the network, why are they continuous values, or like how do they affect what is coming out? Because what is coming out should be just like a categorical variable, like now I'm predicting segmentation, now I'm predicting normals, or maybe am I misunderstanding something?
So first thing, we need to match what the network might accept.
Yeah.
So the network accept some like here it's a 5-dimensional code.
Yeah.
So you want a 5-dimensional code, and this is the simplest thing that you can do, and you are just add it to the network.
Yeah.
And you are trying to find what additive noise or what additive latent directions that I need to add will give me the desired output. And this is maybe kind of unexpected behavior because the model was never trained to generate this kind of images. If you notice, they are unlike real images, maybe except for albedo, it looks something close to real images, but other maps are unlike real images. So the question is it possible, even it is possible to recover this maps or not?
I mean, even some of them have more channels than images, right, like segmentations. You then
That's okay, that's a very good question. So what we do is we still predict 3-channel output and we just average. For depth maps also, we just predict 3-channel output and we just average. And we found that the choice doesn't matter. You can also choose the first layer, second layer, third layer. The results are almost the same. And for convenience, we just use average. And
I think the main, the open question here is because there is no actual equation, like you don't work in 3D, you work in 2D.
yes,
There's no equation that gives a meaning to any of those.
yes,
It could be called awkwardness of the scene, shakiness of the scene, darkness of the scene. Could be called anything, right?
right.
The only way to give a meaning is through the supervision, right?
Right.
It's the only way to give meaning to these 5, like.
Correct. So here we are looking for something what we know. So we know normal depth. So we need some signal or supervision to look for what information we are looking for, because this latent space or is complex and high dimensional, and it's not easy to explore. Only if you know what you're looking for, then it is easy to find. And what we show is that, okay, if you know what you're looking for, it is very easy to find, even though the model was never trained for this task. So here, notice that we are not retraining or fine-tuning the model. We are only trying to find the latent directions that you need to move in order to get this output.
You try to find the directions, or you don't really have an unknown direction problem. You just decide for direction and you supervise.
Yes,
Decide
so
for
that's a very good
specific
question,
latents,
and we
you decide for specific latents,
correct.
and then you supervise that.
Yes, this is what we are doing, and this leads to a very interesting open question which we pursue, but without any fruitful results. Is can we find something what we call unknown intrinsic? As in, we all know from graphics that these representations are not enough to get a exact image that we want. So there are some missing pieces which we really don't know. So can we use the same phenomena to find something that is unknown, but to our experience, we were unable to find
Like
something.
walls.
Exactly. So it's very difficult to find because these latent dimensions are so huge and so complex. Unless you know what you're looking for, it's very difficult to find. But I'll get to an alternate, hopefully paradigm where we can look for such properties.
So in here, this alignment that we are doing is done through a KL divergence, or how is it done? Because the input is really large.
So there is no clear divergence here. There's simple regression L2 loss. That's it. So, and surprisingly, it works, and with only very few hundred images. So what this shows is that this model already has some implicit knowledge about intrinsic images. That's why it is easy to recover them. And there is no complex search procedure, just simple regression loss on few hundred images, and that's it. And we are able to recover this intrinsic concepts.
How big is the decoder for the intrinsic images?
So if I remember correctly, there are 12 convolution layers.
You're in the fire symbol decoder, right?
Which one?
The one with the fire symbol.
Oh, there is no decoder. These are images that you get outside of synthesis network. And at first they are random images.
Synthesis network is frozen.
Synthesis network is frozen.
And so what makes the synthesis network generate both the real image and these intrinsic images?
These are what we are optimizing.
What I'm asking is, so the standard file GAN would generate one RGB image.
Right.
How do we modify it to create these other images?
We simply add a latent direction. That's it.
On the output.
Latent direction on the style code and just pass through the synthesis network. And the output that you get are these images.
Okay, so now this is the question.
Okay.
If we believe that a style GAN generates realistic images,
Right.
how come traversing in the latent direction gives you a normal image?
That's a very good question, and exactly the same thing what David Forsyth told me. This will not work, and but to my intuition, if you think about these images, they are still pixel aligned. They still look like images.
So the only thing being trained here is the star's property direction.
Correct. That's it.
Yeah,
Yes.
so I guess kind of coming back to this question. The supervision storing is deciding upon a direction and then saying this direction is normal.
Correct. And it is, you can think about it, just 512 dimension vector that is good enough to predict all this property maps from a single model. Isn't that appealing? Yeah. Just one model that can generate image, that can give you normal, that can give you depth maps and everything, just by guiding it to find one simple latent direction, instead of training huge billions of parameters model for individual tasks.
I think we should talk about this offline if something doesn't really make sense. As if I'm traversing on the manifold of images,
Right.
how come some directions on this manifold give me depth maps?
It has to, because these are fundamental scene properties maps that makes an image. So if a model has learned to generate images, implicitly it should also know something about lighting, it should also know about geometry, and it should know about something. So what we show is this is kind of the first book to show evidence that yes, indeed, this is the case, and we can recover this. Which I will connect to next point. Is there anything unique about style GAN?
On the page. So the decoder is frozen.
Right.
Here, the only mindful thing is the high latency.
Exactly. Yes.
So have you ever checked that this style guide is not trained on normal image? Or that's
They are not trained on, they're only trained on bedroom images. So style GAN was domain specific data. With diffusion models, you could argue that it's trained on 5 billion images, who knows what is there inside the image. But for style GAN, we know what data set it is trained on. It's trained on just else and bedroom images. So there are no normals inside it. And these are models not trained by us, these are models trained by NVIDIA codes.
But I think you can visualize the latent space. For example, we have the any sampling work in the latent space. For example, if you have the new latent along the direction, you can also sample around that area. And also, what is the training images to visualizing the latent space?
We did that. That's a good question. And what we found is that this latent directions that we find are far away from image space. They are very far away from image spaces. If you look at the L2 norm distance between what makes an image and what produces the surface normals and everything, you can find a nice cluster. They are completely far apart, and which means that you can think of these are like completely different manifold, which the style GAN is able to transform one port to another port. That's why it is able to produce consistent normals for any image. So one thing which I want to point out is that once we find this image, once we find this latent code, you can apply this code to any image with a style gain would generate, and you still get surface normal, depth maps, and so on. So it's not per scene optimization, or it's not, it's once you find it, it just works for every images that a style gain would make.
How large is the latent?
It's a 5 12 dimension vector, and there are 14 layers. So you can, and the latents are injected onto all 14 layers. So the way you see it, it can be 5 12 dimensional, or it can be 14 times 5 12 dimensional, but it's still much smaller than the image space itself.
This can be, on the other side, can be think of a fine tuning. Another kind of small way.
You can think of this, I completely agree with you. You can think of this like a very low level fine tuning, like you're just fine tuning one simple layer with 5 12 dimension. You can think of, there is definitely like 5 12 dimension, but it's surprising that just fine tuning one simple 5 12 dimension gives you this out. You can think this of like you're fine tuning this network, but what we are doing essentially is since we are not learning any non-linearity or anything, we are just simply traversing in the latency.
But have you tested on other kind of things, for example, instead of indoor things, but other also things?
Yes, that's my next slide. So is there anything unique about style gain? So every time when we show this result, so okay, style gain is showed 2022. What about diffusion models? What about other, where it's trained on open domain data set? So this is a new work we call generative models. What do they know? Do they know things? Let's find out. Where we show that it's not just about style gain. You can use any generative model. It can be autoregressive, trained on faces, autoregressive trained on style gain trained on faces, style gain trained on bedroom, or open diffusion models, and we can recover intrinsic images directly from the model. And we use same model agnostic approach. For the interest in time, I'm not going to go in details of how we do it, but the finding is that you can use any generative model and still recover this intrinsic image maps from all types of generative models. So if you look at stable diffusion, it's an open domain world. Here it's like, it's not like bedroom images, it's like some hotel restaurant with lots of tables and scene, and we are able to recover very nice normal depth albedo and shading. So observation so far, lighting and intrinsic images emerge as latent representations. And generative model seems to be grounded in this physical concept. So these are physical concepts. These are not something, these are grounded in physics, like how far away is the pixel, or how light interacts with the surface, and so on. And another finding, what we observed from this work, is that better generative models encode better intrinsic images. So if we test on stable diffusion, different versions of stable diffusions, where we see consistent improvements in generation quality, what we observed is that the recovered intrinsic images also improves. As a stress test, what we did was we also trained a model with random initialization, and we found that it is unable to, it just generates gibberish images many times. Sometimes it can, but mostly it cannot recover intrinsic images. So where the juice is coming from is the representation that the generative model has learned. That's why we are able to recover this intrinsic images.
So let's say that we have two different scenes of the same exact geometry.
Right.
So it's the same viewpoint, same everything, and the only difference is that we have different colors on that geometry. And then that means,
Or lighting.
yeah, let's just say colors. Lighting is the same. And then the two latent codes that you get for reconstructing that image with the gamut are going to be different. And your synthesis network is sensitive to that difference, that delta, because it will be able to hopefully generate these images again with different colors, right? But then if you add a constant offset and project into this like subspace of depth maps, you're going to get two different depth codes that you will then need to decode to the same depth.
Very good question.
Does that collapse somehow?
And we don't, because the different colors or different lights, they are still imaged, they are in the same manifold, or they are in the same, if you think about like a huge blob, it's in the same huge blob, those points, but normal depth are very far away from the image manifold. So small changes like color or lighting doesn't affect normal depth directions. So if you have normal depth different codes, when you apply this very far away latent direction, you don't see any effect. We show in the paper that they are kind of equivalent to these changes, like lighting changes, color changes, and so on. the style and generated normals are still robust. They do not change as you. Okay. So I think I don't have enough time, so I will have to skip some part. So one thing that I want to quickly highlight is that since we know that this lighting and intrinsic images emerge as latent representations, so how about we just treat them as latent variables? Why do they have to be image like maps? So we did this in this work where what we did was we took two images of same scene under different lighting conditions, and we trained a simple shallow unit where what we do is from each image we extract a low dimensional lighting like vector and another high dimensional what we call intrinsic feature map. Do this with the same second image, and they both come from the same network. Now what we do is we combine lighting vector from one image and intrinsic feature map from another image, decode it to produce an image that just looks like the top image. Now you get the self-supervision and you train this model with this simple setup. And once we train this model, what we observe is that, okay, we can relight on arbitrary test scenes. So during training, you saw same scenes in different lighting conditions. At test time, you can have different scenes.
Training is pixel aligned.
Yeah, pixel aligned. Now here you have scene with, they're not pixel aligned, they come from different scenes. The layout is same, the geometry is different. And the model is still able to relight really well. It knows about light sources, it knows about how light should change. And you can see that, okay, the model is able to relight really well. So what was surprising to us, okay, this is good, but what was surprising to us was if we zero out the low dimensional lighting vector, what we get is albedos for free. So albedos emerges for free without even seeing albedo-like images. And quantitatively, should not get into it outperforms all previous models that has that previous method that uses large amount of label data using computer graphics generated data. So this is my favorite example. If you notice in the refrigerator, if you go back, you can't rarely you can see all the items in the scene. And if you look at the recent intrinsic image diffusion paper, they are unable to get the albedo right. And if you notice you know that okay, there is a ketchup bottle here, you can see all the details next. And if you apply simple piecewise constant constraint, you can get like a piecewise smooth albedo that you look for. So these naturally emerges inside the model without seeing any albedo-like images during training. So coming back, what about the question that we started with? We want to relight real images, not just generated images. So this latent intrinsic representation show that, okay, we can relight arbitrary scenes. But how about combining this with powerful image generative models? The previous one did not use any generative model. So this is a new work which appeared last night on Archive. We call it Luminate, where this latent intrinsic meets this powerful diffusion model. So I'll skip how diffusion model works in the interest of time. So I just want to highlight that this diffusion models are able to construct scenes given noise. And we now also have nice conditional models where you control net, where you can give conditional input, like you take an image, you get a depth map passed to control net, and you get a different scene with respect to the depth map. So what we do in this work is that we combine this, we take this latent intrinsic representations that I showed you earlier, and combine this with a modified control net, because this is a latent representation. These are not image net, these are not image like maps, and then feed it through a diffusion model, which gives you the relit image, the same image that you see in the scene. But the problem is this lighting vector is very low dimensional. In our case, in the latent intrinsic paper, what we did was we just used 16-dimensional vector, which is not what this diffusion model accepts. So diffusion models need something like thousands high-dimensional vector. A simple solution that we found is that you can simply train an MLP to map this low-dimensional vector to high-dimensional vector, and then feed it through the latent control net architecture. And also what we found is that if you feed this lighting directly into the diffusion model, it seems to help us, and it seems to do a reasonable job at relighting. So this is a simple setup where, again, you take two images, pixel aligned, same scene, different lighting, you get a latent intrinsic representation, pass to diffusion model, and relight it. And one thing to note here is that we don't have good reliable data set to train this model. So what we do in this paper is that we use the StyleGAN relighting work that I showed you, and we curate synthetic data set to train this model. Now, if you train this, what we find is that we can get in the wild indoor relighting. At the top right, you see a target light. On the left is a source image. On the right is a relit image. So notice that this is a nighttime, and there is an invisible lamp, which we don't see. In the target image, there is a direction light coming from the window, as evident from the reflections on this painting. And the relit, you see that, okay, we have converted nighttime into daytime, and it also has a direction light. Things to notice are there is a pronounced gloss on the table, there is a shadow. And what struck to me was something which I said is beyond imagination, is that if you notice this TV screen, can anyone tell what it is? Sorry? Yes. So if you notice carefully, there is a reflection of the table. Going back, there is a reflection of the table, which is
This reflection correctly like it's not correct.
it's not completely. I completely agree that it is not completely physically correct, and we don't know how to evaluate it. But this looks very plausible.
I mean, the vertical line in the middle of the TV crosses exactly the middle of the table. There's no way.
So the camera is pointing downward into the scene, and the light is coming from the top.
See the window, not the table. The table is exactly on the normal of the TV. If the table is exactly on the normal of the TV, and we are off the normal, there's no way that we see the table.
The table is also reflected into the fireplace.
The table is also reflected in the fireplace. Yes. The different part of the table is reflected in the fireplace.
Correct. That's correct. Because we look in this direction. That's correct. We are about the same, but in the TV, we should look at the window, not at the table.
We should look at both where the camera is and where the light source is coming from. It's dependent on
Just normal to the TV shows to the table. Normal to the TV shows to the table. The table, only if we are at the normal, we're going to see the table. But let's close.
Yes, we can. It's okay. Let me put it in this way. This is not perfect, but you see some hallucinations that it seems plausible. But I'll get to that. I'll get to it in few other images where I can convince you that, okay, it's doing the right thing. The other thing to notice.
The conversation of the screen
The other thing to notice here is the strong shadow that you see of this TV stand. Okay. So this is a very hard, this is something like there are some pet images that you have that you want to really stress test your model on. This is like one of the scenes that I really want to test this model on, as it's very complex. There is a transparent glass table, there is a lamp, there are so many different elements in the scene. And here is our relay. First to notice is that it is able to suppress the gloss that you see on the table. And the second, since the light is coming from the light, you can notice that there is a gloss, there is a strong gloss coming from the window over here. And the other thing to notice here is, again, what do you see?
The lamp is changed in shape. They are not the same lamp.
They're not the same lamp, exactly. Yes, they are small local changes because of the stochasticity in the diffusion model. But what about the lighting changes?
The left is the synthesized from the right is synthesized.
How about now? So if you notice, there is a shadow of the lamp onto the wall. Okay, these are again plausible. We don't know, we don't have ground truth to evaluate whether this is not, but this is something very very surprising. And so far, at least to my knowledge, we don't have any model that can even relight something like this for indoor scenes. Okay. I'll skip this. This is one nice video. You can, we can also like switch on lamps and everything. And also we can change with different lighting conditions, we can change the lighting different. You can get different lighting of the same scene. All right. Okay. So I'll skip this part in interest of time. Quantitative metrics, we also evaluate on quantitative metrics, and we find that we get like over 35% improvement on this controlled data set. This is hard MIT multi-illumination data set. You can see that strong lighting changes. And for relighting, we get about 30% improvement from previous method. Quickly in 2 minutes, in 2 minutes, I want to now switch gears. Okay, I showed that, okay, generative models can do so many great things, but what about what they can't do? Okay, so we have this realistic generated images, but if you notice carefully, there are shadow errors. The shadow of this person is disjointed, right? And here, in this case, the shadow of this coffee table is incorrect. And if you also look at perspective vanishing lines, if you draw these vanishing lines, okay, here they meet at vanishing point, but if you draw more lines, they don't meet at the same vanishing point. Same thing in the other scene, if you draw lines, okay, they seem to meet, but if you draw more lines, they don't meet. So this generative model seems to make this perspective errors, which we can exploit. And this is what we do in our work, where we test generative models on shadows and projective geometry lines and show that generative models don't really understand this. And we can use this to detect generated images. So here is a detected shadow error from our model. As you can see that it is able to reliably detect the errors in the shadow. Here are perspective errors. As you can see that it is able to detect the errors. Okay. So we use a classifier, then you use the grad cam to see why the classifier thinks that the image is generated or real. So what we do is we use 3 geometry cues. First is, like I said, object shadow cue. You use off-the-shelf model to predict object shadow, object mask, and shadow mask associated with each object. And you simply train a classifier that takes only this input. We forget about the images. Only takes object and shadow, train a ResNet classifier, and ask whether it is real or generated. And you do this on a bunch of real and generated images. And once you do that, what we find is that we can reliably tell whether an image is generated or not, even without looking at pixel information. Another cues that we use is perspective cues, where we use an off-the-shelf perspective field model where you can recover like per pixel where the gravity vectors are and how far away each of the pixels are from the horizon. And you train again a simple classifier to tell whether an image is real or generated. We also train another cues where you simply detect line segments that are in the images. And you train a point net. You can think of this 2D line segment as 2D points. Instead of 3D points, you can train a simple point net and tell whether it is collection of points, collection of lines, and tell whether it is real or generated. So we evaluated extensively on different models, including state-of-the-art stable diffusion, Deep Floyd, DALI, Firefly, and so on, over 1 billion indoor images, 500K outdoor images. And what we found is that all generative models fail at replicating projective geometry. We can detect these generated images with about 98% accuracy. Here are some interesting examples that I really like. I mean, I'm showing this. Of course, these are generated images. So if you notice, there are here, the shadow looks correct, but the perspective lines are wrong. So our shadow classifier thinks that it's a real image, whereas the perspective classifier thinks that it's a generated image. At the bottom, again, okay. Any guesses why something is wrong? I'm 100% confident that David would have showed this result. David would have showed this image. Anyone? So if you notice, the shadow of both these shades are in 2 different directions. If this has to be real, it has to come from a planet, at least there are 2 suns. Right? They're not pointing in the same direction. All right. Okay. So to quickly conclude, we tried this on Sora. Even Sora has this problem. Like Sora images, even Sora video models that we have, the most powerful generative models, it still fails to replicate projective geometry. So to conclude, what do generative image models know? A great deal of unexplored knowledge about scenes. They seem to understand our visual world in some physical plausible way, but they do make interesting mistakes like this projective geometry cues. So what's next? I think in next 5 years or so, I believe computer vision will most likely be like how previously we did observational science. We had some models which we observe and try to understand phenomena that they are doing. And we will derive solutions to it from well-trained generative models. The other big questions are, how do we impose projective geometry in generative images? So this is like 98% accuracy is something very astonishing. How can we impose and improve these generative models? And can we find other knowledge that these models know about, let's say, gravity, dynamics, and so on inside this model? Do they understand any of this, or is there any gap that we need to? With that, I'll conclude, and thank you so much. Thank you for having me over here, and thank you for attention, and sorry for taking 5 minutes over.
Thank you, Anand. Really very stimulating talk. I mean, I think the PG must be convex, so that's why in that image. But really excellent questions. Questions from the audience here.
Have you ever tried to visualize if you, for example, for the relighting, like the contributions without you showed the source lighting, maybe you can have a synthetic, like maybe a continuous changing light, and how the generated like image will change.
So for that, we did, there is a data set called, you don't have to go to synthetic, you can use MIT multi-illumination data set, where they have 1,000 scenes in 25 different lighting conditions. Let me quickly, you can find qualitative results on archive. So this is a quantitative evaluation where we have the ground truth, where we know what the relit image should look like. So you have a source image, you have a relit image, and these are taken in calibrated setting. So different scenes will still have same lighting configuration. So there are like different light, it's a stage light setup where you switch on or switch off light source and everything, and you capture the light. And you can use the data set to relight and compare with the actual ground.
I mean, this quality this current I understand, but I mean, usually people evaluate some like nerves and this kind of synthesis by continuously changing, like linearly, like you continuously changing the light and see continuous changing of to see the artifact.
Yeah, one of the limitation is that like StyleGAN, still diffusion models don't have this nice linear interpolatable space, so we can't do this linear interpolation. Second thing which I disagree with is that synthetic data is again a not good way to evaluate, because with synthetic data you again make some or other assumptions, either from rendering engine or from the physical model that you use, and that does not clearly resonate with the real world lighting that you see. I think a better way to evaluate is mostly by using real world images. There is only one such data set, so it's a good opportunity if we can curate more such data set for lighting tasks. We have abundant multi-view data set, but we don't have multi-light data set. So this is probably a good opportunity to explore. One, and second thing I want to say is that right now we still don't know what is a good metric to evaluate lighting. So this RMSE, SSI, maybe it's only looking at per pixel score, but it's not looking at the global lighting reasoning. The only way we could do right now is human evaluation, and this is what we do.
Your last,
No, I mean,
Yeah.
go ahead.
your last work, I really like the last one. And you detect like these arrows in the generated models. How do you fix these arrows?
It's a very good question, and it's a ongoing work. And so far, the evidence that we have right now is that we need big architectural changes, because the models the current models are not capable of doing long scale spatial reasoning. So if you think about this projective geometric use, most of the time the light source is not visible. It's away, it's outside the image pixel. And even the line segments that you see, they may be coming from right corner and left corner. And we don't have a clear mechanism of interacting with each other. Attention maps are there, but they're still not enough because attention maps are mostly focused on finding similar patches. And most often the way the images are constructed is that you find similar patches mostly in the center of the image, in the neighborhood. So there is no way of having a clear interaction between, let's say, the top right corner and the top bottom left corner. So we need some architectural innovation. So we have a follow-up work where we show that if you impose projective geometry via laws, like explicitly train the model to have these properties, we can reduce from 98% to 86%. So we get like 12% improvement, which is significant, but still 86% is 86% of generated images you can clearly detect only by looking at projective geometric use, not even looking at pixels. So there is a long way to go, and I think we need the current architectures are not capable, and we need something to do about it. And I don't have a solution, but I think this is the problem that we have identified based on our experience.
So, I mean, when we ask the question, I mean, the very good question, but genetic model now. But if also we want to achieve reliability, why don't we get like foundation models like that, etc., which know very well,
Right?
Stuff, produce the depth in the models, and have them as an input in the reliability. Because this is what the graphics person will do.
Right, but still you want to generate an image, right? How do you do that? Either you extract this inverse graphics representation, put it in a graphics engine, and then render it, or you still train a neural network then.
That will probably generate an image with pretty good maybe depth. Maybe vanishing points does not make sense, but roughly I could get a pretty good idea about the normal depth.
So the Generative work that I earlier talked about kind of uses that. It uses some pre-trained network, not SAM. SAM is the recent one back in 2022, whatever the latest network was. They extract this representation, inverse graphics representation, and then render it. The problem with all these approaches is that if you have many models interacting with each other, errors in one can have a catastrophic effect in the other one. And the accumulated errors is very difficult to control. If you have one single model that is able to do it, then it is easy to control, in my opinion. But it's an interesting question. I don't have an answer to it. Maybe you can use SAM representations, extract it, and train inverse graphics network to render an image, but we don't know yet. To me, generative models makes more sense because it is learning to generate images. And the conditional generative models that we have nowadays, you are making small changes to the images. Even though the lighting changes are global, they are, and we show that, okay, it's still possible to make these changes. So in my opinion, generative models are a better choice, but I would be happy if something else works better than the generative model. All I care about is what works best. It's not that either it is generative model.
All right, any other question? Thank you very much.
Thank you again. Thank you. Thank you so much. Thank you. Great audience. Loved the energy, questions, interactions.
Yeah,
I had to rush at last minute because it is good to have questions and.
Hello, I'm Pratik.
Hi, it's nice to meet you.
Very nice results.
Thank you so much.
It reminded me of, I think the reason we are getting these new depth maps, etc., style canvas is related to the universal adversarial perturbations kind of ideas. I don't know. If
I am not aware of those.
So,
Can you?
I mean, in the adversarial perturbation literature, people kind of discovered that you find one perturbation for every image by gradient descent.
Right.
But you can find like a perturbation that perturbs all images in one data set,
Right.
but for all networks.
Oh, for all networks. Very
So
interesting.
that is why they call them universal perturbations. And
I see.
I think these are basically like null spaces of the feature space.
Right.
So your 5 and 12 dimensional space, not all of it is populated because we don't have enough samples to narrow down the space. And then these are null spaces in which you have to move,
Mhm.
which your embedding vectors secretly now fill with your supervision.
Mhm.
This is my understanding after looking at the slides.
Maybe, yeah, there may be some analogy over there. And the
That's
only
clearly
thing,
like
what is still, I mean, in retrospect, it makes sense. Okay, this model's learned to generate images, so it should know something about physical properties. But at least David's comment was why this will not work is that the discriminator would never allow to generate something that does not look like image maps.
this is exactly what I'm saying. So what is happening in this method is not that the depth image is present on the manifold or close to it. What is happening is that the embedding vector concocts it
Correct,
by
exactly.
training,
Yes,
by your training.
by
So
you can call it
what
training by simple training, by
Yes,
like simple.
Yeah, so what I'm saying is that your mechanism to understand